Are you facing difficulty while implementing multi-class segmentation? If yes, then watch the complete video. In this video, we are going to build a human face segmentation project where we are going to input the human face and the model is going to predict a multi-class segmentation mask. Hello friends, welcome to this video. This is Nikhil Tomar and you are watching Idiot Developer. Make sure to subscribe the channel and hit that bell icon for more such videos on deep learning and computer vision. So first of all, let's take a look at the dataset. So the name of the dataset is Landmark Guided Face Parsing Dataset, in short LaPa, and it contains more than 22,000 facial images. And here you can see some of the samples. So dataset contain images, their respective human facial key points, and the segmentation mask. So for this video project, we are going to take the images and the segmentation mask and build the entire project. So to know more about the dataset, you can have a look at this paper. Check the description for the link of the paper. Now let's take a look at the files and the folders. So first of all, we have three folders, that is test, train and validation. So these are the three splits which we mostly do with any deep learning training. After that, we have some text files. So first of all, let's take a look at the text file. Here you can see in this file we have this label, that is the pixel value of each of the label and its respective RGB code. Okay, so in short we can say we have 11 classes. Now let's take a look at the second text file, and here you can see the label and its respective class. So here we have name of all the classes. From the class we can easily see it parts the human face very deeply. See, you have skin, left eyebrow, right eyebrow, left eye, right eye, nose and all things. Okay, now let's take a look at some of the samples from the split. So let's go to test. So within each of this folder, test, train and valid, you will find three subfolder. First would be images. Here you can see some of the samples, and these images are mostly square. If you see, you feel like a mostly square. Okay, not every image is 100% square, but in short, so from this we can say we're going to take on an average size, let's say 256 by 256 or 320 by 320, or let's say 512 by 512. Next we have labels. So labels basically refers to the segmentation mask. So this is kind of blackish mask because the range of the pixel values are from 0 to 10. So this is why maybe you cannot see it, or if you just give a bit more focus you can see. But here on my screen I can see, maybe because of YouTube video compression or recording you cannot see, but we'll see them while we work on this data set. Next we have landmark. So let's take a look at the landmark also. So it's basically a text file which has 106 points. So these are the points for the landmarks. Maybe in future video we'll work on the human face landmark also, and we can also do a joint project of landmark and the segmentation mask. That would be much better, but for now let's just focus on the segmentation only. So this is about the data set. Next we are going to implement the UNET architecture in the TensorFlow framework, and this is the architecture we will use with our human face segmentation project. So let's now move on to the implementation part. So first of all, we are going to import all the libraries and especially the layers from the TensorFlow. So here you can see we have imported most of the layers from the tensor.keras.layers. Okay, then we have imported this model which we're going to use later. So first of all, let's implement the convolutional block. So if we take a look at this UNET architecture, here you can see, if you remember this arrow, these are cone with 3 by 3 and ReLU. So this is a common block. If you see, it is common in the entire unit. So first of all, we are going to implement this and we're going to call it conv block. So this conv block is going to take the inputs first, then it's going to take the number of filters. So number of filters refers to number of output channels. So first of all, we have a convolution layer. First we're gonna give number of filters, then the kernel size, that would be 3 by 3. Then padding would be same, and input, that would be inputs, the argument we have taken with this con block function. So next, if you see the original paper, there it has ReLU layer, but here we're going to add the batch normalization. That is the standard for now. We use a normalization layer, that can be any normalization, but batch normalization is most commonly used. Next, we're going to use the ReLU activation. So we have 3 layers. So we're going to copy them and paste them, because we need to repeat those same set of layer again. So now our conv block function is complete. See, this is very simple. Now we're going to move on to the encoder block. So encoder block would take the input, that is the input feature map or the output from the previous block. Okay, the number of filters. So in encoder, first of all, we're gonna call the conv block. Okay, we're gonna say x equals to conv block, first inputs, then number of filters. Next, we're gonna call the max pooling, that is 2 by 2 max pooling, to decrease the height and width of the feature map. Because if we continue with the same height and width, the number of parameter and the time consumed would be huge, and that would affect the training, because it's going to take really long. And also with max pooling, we get the maximum, like we get the max features, and we believe that those max feature are better. Okay, so let's do max pool 2D. So initially, if I tell you that why are max only taken, because those give better performance, just that is the reason, because no one knows what happened inside those layers. Okay, that is just a black box. We only theorize and just say that this happened, and we do some experiment, then that supports our hypothesis, then we can say, but still we don't know what happened inside that. Okay, so this is just theory. Okay, in my perspective, no one knows what happened inside those layers. So okay, here we have the conv block, and then we have the max pool. So here we're going to return both the thing, the output of conv block and the max pool. So output of conv block would act as skip connection. If you see these arrows, these are skip connection, that is the output of conv block. Okay, and this output of max pooling, if you see max pooling 2 by 2, this act as the input for the next encoder block. Now let's try to build our UNET architecture. Build UNET. So this function is going to take 2 arguments, first input shape, then number of classes. And if we remember, we have 10 plus 1 class. So 10 plus 1, why 10 plus 1? 10 main class and 1 for background, because background is always there. So that's why sometimes it is referred as n plus 1 class, n main class and 1 background class. So let's define our input layer. So it's going to take input shape. Okay, now we need to call our encoder block. So here we have 4 encoder block. So encoder block gives you 2 output, first x, which is a skip connection, and p, the pooling. So we're going to say s1, that is first skip connection, and p1, first pooling output. Encoder block, input would be inputs, that is the input layer, and number of filter would begin from 64. Like this, we have s2, then p2, encoder block, input would be p1, and number of filters would now increase by factor of 2, that is 64 into 2 became 128. So if you see in the entire encoder, the number of filters increases by factor of 2 and the height and width decreases by a factor of 2. Then we have s third and p third, encoder block, p2, then 256. Then we have s4, p4, encoder block, p third as the input, then 512. So I hope you are getting this, because I'm doing it a bit fast. So this is our encoder block. Okay, so first of all we have the input layer, then first encoder block, it's gonna give 2 output. First is a skip connection, that is output of convolution layer. Second, output of pooling, So output of pooling would act as input for the next encoder block, and that is what happened in the rest of the encoder blocks. So this is about the encoder. Now in between encoder and decoder we have a bridge, that is a simple cone block, and that cone block would take P4 as the input, and number of channel would increases by factor of 2, so those would become 1024. Now comes the decoder block. Okay, so decoder block is a bit complex, not very complex, just a bit complex as compared to encoder block. Okay, so let us define, and will easily go through the decoder block so that you may not get confused. So decoder would take two input. First is the previous input feature map, and here the first decoder block would take B1 as the previous feature map. Then it has a skip connection. Remember these S1, S2, S3, S4. So these are the skip connection. Then number of filters. Okay, so this is our decoder block. So first of all, we need to call a transpose convolution layer. I'm going to paste it directly here. So this is con 2D transpose. So what it does, it take number of filter, kernel size, then here we provide a strides value of 2. So stride value 2 means just increase the height and width by factor of 2. So here it learns how to increase the height and width. So over the time in the decoder, it's going to learn how to increase the size and what features to add so that we get a high quality segmentation mask. And because it's a multi-class problem, so it's need to do extra work. That is why I believe in the initial decoder layer, conv 2D really helps. Okay, because there are other techniques to increase the height and width. That is, bilinear upsampling is mostly used. That is also really good. Like I mostly use bilinear upsampling in my research papers, because the learning part also gonna do by the other conv layer. Okay, but this is also good. It's not that bad. It's just up. It's your choice. But here we are working with UNET, and in that paper it has used transpose convolution. Now what we do, we're gonna give it the input, that is this inputs. So now we're gonna call our decoder block. Okay, before that let me just call this function in the below just to check how this function build unit is working. Okay, so first of all we need an input shape that would be, let's say, 512 by 512 by 3, because we're gonna read the image as RGB. Then we're gonna call build unit. We're gonna give the input shape. Number of classes would be 10 plus 1, 11. Okay, now it's done. So now we're gonna print shape of some layers. First would be B1 dot shape. Then we're gonna print the shape of all skip connection. S1 dot shape, S2 dot shape, S3 dot shape, then S4 dot shape. Okay, these are because you need to have an idea what the shapes are, then only it would be easy for you to understand this decoder block. So that is why we are executing this function and printing their shapes. So let us now just try to run our program, and we can also see if we have any problem. Okay, here you can see a lot of lines from the TensorFlow, and this is one of the most common thing. So there's a way to remove these lines. I'll show you. And here you can see the shape of the B1, that is 32 by 32 by 1024. And here you can see skip connection. The shape of first skip connection is same as the input image, that is height and width are same. Then decrease by factor of 2, then again decrease by factor of 2, then again 64 by 64. So first of all, let's remove these lines. So what we need to do, we need to import the OS library. Then just simply write this line. Like over the time, I just really learned this long variable name and thing. Now I don't even need to recall it. It's my finger just simply type it. I can see nothing is there. We simply see our output. So this makes it really easy for us to see. Like initially, if you are a newer guy, you would be confused. What is this? What is it? So this is nothing. Just don't worry about it. It just basically give you some of the information that this is, and at last it's going to give you GPU. Your device 0 is NVIDIA GeForce RTX 3090. Okay. Now let's come back to our shapes. So this is the shape which is gonna get, which is gonna be an input to the decoder block. So let us call our decoder block here. Till now it don't give any output, so we not gonna write at D1. So first of all, it's gonna take a previous that is B1. It also required a skip connection. For now, I'll just type S4 and I'm gonna tell you why S4. Okay, the number of filter would be half. From here in the decoder block, the number of filters would be decreased by a factor of 2 and the height and width would increase by a factor of 2. Okay, so that would be 1024 by half, that is 512. Now here we're gonna print the shape of X. Okay, now just remember all these shapes. Okay, here if you see, this is the input B1, 32 by 32. It passes through the transpose convolution. It became 64 by 64. Now after this convolution, this transpose convolution layer comes the skip connection. We need the concatenation. So what we're gonna do? So just take a look at this height and width, that is 64 by 64. So we need a feature map of this exact same height and width, not the number of filters, just height and width. So see all this skip connection. We see the last one, it has same height and width. So we can use this feature as a skip connection and just concatenate it. That is why I've put S4 here. Now what we can do, we can say X is equals to concatenate. We can say X then skip. So this is done. Now we're gonna print shape of X again and we're gonna run it. So here you can say it is 64 by 64 by 512. Now it is concatenated with the skip connection and it became 64 by 64 by 1024. So by default it concatenate on the last axis. That is why we don't need to provide axis here. Okay, now comes the convolution block. Okay, X then number of filters. So this completes your decoder block. So that is really simple, just that you need to have a bit of understanding how these, which skip connection to take and why only that one. Okay, now we can say D1. So we have 3 more decoder block. D2 decoder block, input would be D1 now, and skip connection will be S third, because again this is gonna get upsample. Now it would become 64 became 128 and this S third has 128 by 128 shape, and 512, that is number of filters, would now become 256. Let me just copy it and we're gonna change the name to D third. Input would be D2, skip connection S2, number of filters 128. Again we're gonna paste it. This time it would be D4, input would be D third, skip connection S1, and number of filter 64. So we are done with the decoder also. So decoder just try to learn the features which are useful in generating segmentation mask. So now we just need an output layer. Okay, so output layer would basically be a 1 by 1 convolution layer. So now number of features in the output layer would be equals to number of classes, because each feature would represent a mask for each class. Then 1 by 1 as the kernel size, padding equals to same. Then here activation would be softmax. And input will be D4. So just remember, when you have more than one class, the activation function would be softmax. And when you have one class, this when you are working in binary segmentation, so it only gonna use a sigmoid as the activation function. So this is our architecture. So we have both the input layer and the output layer. Now let's build our model. So let's call our model here, and here we're going to say model dot summary. So we're going to print the summary of the UNET architecture. Here you can see we are the last, and it give you total parameter, then trainable parameter, non-trainable parameter. And if you see the last layer, it is 512 by 512. So just remember, the shape of your input should also be equal to your output, especially the height and width. Okay, just remember that. That is why shapes are important when you are designing an architecture, so that you can concatenate, add, subtract, do whole lot of things. So it is essential to think in terms of shapes first. Okay, first think in terms of shape, design the architecture, then think in terms of feature, how the feature would propagate, what happen when we add them, what happen when we concatenate them. Okay, this is the second step, like how I work. Basically, I'm telling you the way, like how I work. This is not that you need to follow the same thing, but from my experience, it's better to think in terms of shapes first, so that you can design the architecture. Okay, so that you don't have any error while doing adding layers and things. When you add layer, just think, let's say we have concatenation. So first we think their height and width should be same, then only we can concatenate them. Then think whether concatenating those two features would be good or that would be bad. Okay, like this you're going to think in two ways. Okay, so this is about the implementation of the unit. Now we'll work on the training part, where we're going to take the dataset and train our unit architecture. So first of all, let's do the same thing, import all the required layers. So first we have the OS library, then we have the same line to get rid all the TensorFlow lines. Then after that we have NumPy, because we are dealing with arrays. Then pandas, maybe it would be required or maybe not required. Then CV2, this is OpenCV, used to read, resize and write the images. Then we have globe, so this is going to be used while loading the data set. So we just give a path to it, basically a pattern, and what it does, it's extract all the paths which match that specific pattern. Then we have, I don't think we require this, so let me remove all the known libraries, we can later add them. Then we have train test split, we also don't require this because we already have the splitted data set. Then we have imported the TensorFlow. After that we have imported these 4 callbacks which we're going to use while training. So these are really helpful. Okay, I'll explain each of them when we come to that part. Then I've imported the build unit from this unit file. You see, this is the name, build unit. So now we need some global variables first. Okay, so I'll just directly copy paste them here, that would be time saving. So these are the global variables, so we just write them here so that any function can access them. Okay, so first is the image height, then image width, number of classes, name of classes and the RGB code. Okay, so we just write them here. After that we gonna have a function, we would have a function to which we're gonna give a path and is gonna create that path. Basically it is used to create a folder in simple term. Create dir, we're gonna give a path. So first we're gonna check if that path exists or not, or if that path does not exist, then create that path. Now here we say if not, path exists. So if that path does not exist, then make that folder. Just a simple function. So we're gonna have a blank folder where we're gonna save our weight file and our other log files. Okay, now next let's write a function to load the data set. So we're gonna have the dataset path. So I've already shown you the dataset. Let me just show you again. So this is the dataset. Here we have test, train and validation, and each contain images and labels subfolder. Okay, so let us just try to extract images and labels, or you can say the multi-class mask. Okay, so let me just write like this. Now we're going to say train x. So train x refers to training images. So x here refers to images and y refers to labels or the mask. So we're going to use globe. Inside that we need to provide a path. So first path would be the dataset path. After that we want to have training images. So train that is name of folder, then images subfolder. Then we want a pattern, we want all the images, so we want to give a pattern that would be star, refers to anything, so it should start with anything and should end with .jpg. So this basically means get all the files which have this extension. Just see how simple is that. Then we're going to sort it because it's going to give a list. Okay, and both the images and mask would have same name, just extension is different. That is why we sort the list, so we get all the name in a proper order. Then we're gonna have train y, so simple, we're gonna rename it, and instead of images we're gonna say labels, and here they would be in .png. So this is how we're gonna load the training images and mask. We're gonna copy the same, or I can directly copy paste them here, the validation and the testing part. So this is how we load the validation, then the testing. Okay, so now we have the images and mask for the training, validation and testing. Let's now give them back the function. So this is the function where we load the data set, and now we're going to write a function to read the image and mask. Let's say we get individual image and mask path, so how do we going to read them? So let's define a function called read image mask. Simple. So x and y, just image and mask path. So first of all, let's do an image. So we're going to call image as x, cv2 dot I am read x, that is path. Then we're going to read it as RGB. Now we're going to resize it. Now if you see, why have we defined these variables at the top? So that we can access them. Now we can easily access them. We can simply say image width, then image height. See how easy it is. Then we're going to normalize the image pixel by dividing them into 55. Then we're going to convert it to float 32. I know by default it is float 32, but still we will explicitly define it so that we are sure. Now we're going to work on the mask. So we're going to read the mask as grayscale first, not the first, is grayscale only. Then we're going to resize the mask. So let me just copy it from here. We can simply change the name to y. Even like I got confused, x and y, but it's really easy. Otherwise you have to write long image mask. So that is why I mostly do x refers to image and y refers to mask, as simple as that. It's just kind of when you say y is equals to f of x, so that is what deep learning basically is. Y is your refers to output, that is mask, which we require, and x is the input, that is the image for this. Now we're gonna say we're gonna change its data type to integer 32. So why don't we normalize the mask? You may ask this question. Because our masks are already normalized. I have already given example. So just see again, because these are already normalized. The pixels range are from 0 to 10. Okay, that is why we don't normalize them, because they are already normalized. We just now need to convert them to one hot encoding. Okay, and that is we're gonna do later. But for now, this is the way. So when you have a normalized mask, don't normalize it again, because it's already done. So let's say you RGB mask, then you need some way to normalize them. Okay, so now we're gonna give these x and y back because we are done. Now we're gonna build some functions to build our dataset pipeline. So first is our pre-process function. It's going to take x and y, that is image and mask path, because this pre-process function would be used inside TensorFlow. Okay, so these x and y path would be encoded. Okay, so inside it we have another function called f. Again it takes x and y, the same image and mask path. So let's decode them first. Then image, mask, or we can simply say return read image mask x comma y. Just this simple function is done. Now see, we have used OpenCV and NumPy here, and those are not the part of TensorFlow. So you cannot directly use those functions here. That is why we have built this function. Then we have built this pre-process, and inside this pre-process, we're gonna call a TensorFlow function called tf.numpy function. With this function, we can use any function which is implemented outside the TensorFlow. So we're gonna say tf.numpy function. So first of all, it's going to take the name of the function, that would be f here, f. Okay. Then what are the input to that function, the f, x and y. Then what are the output data type? Those would be tf.float 32 and tf.integer 32. Done. Now this function is going to give you image and mask. That is a tensor. Now this mask is normalized. We need to convert it to one hot vector. So what are we going to say? tf.one hot mask and number of classes. Simple. It's done. Next we need to set shape to those image and mask. So we are done. Now we're going to give those image and mask back. Next we are going to implement another function for the dataset pipeline called tf dataset. Now it's going to take x and y. So capital X, capital Y refers to list of images and mask. Okay. Batch 8. So this is the default value of the batch size. Next we have this tf.data.dataset, then from tensor slices. Now we need to give those x and y. Then we're going to say ds is equals to ds.shuffle. We're going to shuffle the data set, and let's give a buffer size of 5000. Maybe large buffer size required because the data set is large, but let's give it that. We can see it later. Here in the map, we're going to call this function, that is pre-process. So this entire function just take the image and mask path and give you the image and mask tensor. So that is why we have just first this individual function, then inside another sub function, then another function. This is just to done so that we can easily call it here. Maybe you can use TensorFlow things which are defined inside it, but I believe, like, I mostly use OpenCV and NumPy. I just feel much friendlier with them. I don't feel much friendlier with those TensorFlow things. Okay, that is why I use this OpenCV, NumPy. Then we need to set the batch size, batch, the value. Then we're going to set some prefetch. Let's say 2. We're going to give this back the ds. Okay, so we are done with the function. Now we're going to work on the execution. So first of all, what we're going to do, we're going to seed the environment. Okay, to make sure we have same randomness, so that randomness does not change every time, because during testing and training it is better to have same set of seeds. Otherwise your result may be different every time you test, and that is not good, because reproducibility is really important in deep learning. Maybe in one inference you get high performance, in second you get low performance. How you gonna test your model? That is not good. That is why we seed the randomness. Maybe there's other library you can seed. There's just make sure you have seed the randomness. Just sure. That is the thing. Next we have built a folder called files, which would save our weight file and log file. Okay. Next we have some set of hyperparameters. First we have image height and width, that is we're going to set to 512 by 512. If you see, my GPU is 3090, so I can support this image size. Maybe for you the GPU is not that good, so you can decrease the height and width. Say like 256 by 256 would be like optimum, not that small, not that large. Or maybe you can go with 128, or you can just do one thing, just crop, maybe somehow crop those and convert it to 128 by 128. But I believe if you have a low GPU, just still have 120, It's 256 by 256 as a size. Then number of classes, then input shape, that is image height, image width by 3, that is 512 by 512. Then a batch size of 8, learning rate 1e minus 4. So 1e minus 4 basically refers to 0.3011. Then number of epoch 100. So 100 will be really large for this video tutorial. So we're gonna train it to just one epoch only. Maybe that would not be one day because the data set is really large. Okay, you're gonna see. Then we're gonna have some paths here. Okay, the first would be dataset path. So let me just write it here. Path. So first we have is dataset path to our dataset, that is LaPa, landmark facial point something face parsing dataset. Then we have model path where our weight file would be saved, that is files, the folder which we have created. The name of the weight file would be model.h5. Then again we have a CSV file and we're going to name it data.csv, in which our training scores and loss and everything would be saved. Okay, so we are done with the path. Next we have RGB code and the classes name. Okay, so I have just copy pasted them from that file. You can also do the same, or if you are much better in terms of code, you can just write the code. Maybe even I can write the code, but I feel this is much better. I just try to make sure the video is simple, because let's say your data set is different, but you can simply copy paste them here. Okay, if I write some code you may get confused, but it is easier. Okay, that is why I have simply just make a list out of it. Now we're going to load our data set. Okay, so I've called this function load dataset, given it the dataset path, and we have our test, valid and training. Okay, so let's now do one thing. Let's run the code. So here you can see the size of the data set is, we have near about 18,000 images for training, 2,000 for validation and 2,000 for testing. So this is really huge data set. I believe it's going to take good amount of time for training, and even for testing 2,000 images, that to a 512 by 500, it's going to take good amount of time. Okay, so let's don't worry about that. Let's now work on the dataset pipeline. So this is the function, that is tf dataset. Inside it we give training images path, training mask path and a batch size. Then we have validation dataset. We give validation images, their mask and a batch size. So we are done with that. Now I'll just show you. Okay, x and y in training dataset, train ds. Now these x and y are basically batches of image and mask. So I'm going to print their shape and I'm going to show you. So let's break it here. Okay, let's not break it, and let me just show you how it runs if I don't break the loop. So this is basically batch of images and masks. You're gonna see, you can see their shape. So 8 indicates the batch size which we have specified here, if you see. And if you see next, the height and width, the number of channel, and same for this mask, height and width, number of classes are 11, and this 11 is basically from this one hot step. If you remember this one hot step, till now this mask has only one channel, but when you pass it through this one hot, it became 10 plus 1. Okay, so it has 11 classes. You can see these are the batches. Let me just close it down for now, because this is just to show you. Okay, so we can remove this. Now we're gonna build our model. So let me copy paste it here. So here we have our UNET architecture which we have implemented. So we're gonna give it the input shape, number of classes, then we're gonna compile it. So we're gonna give it the loss, that is categorical cross entropy. That is the loss which you will use while you are working with multi-class segmentation. When you are working with binary segmentation, here you can say binary cross entropy. And our optimizer would be Adam. You can change it accordingly, but I prefer it. This is my default optimizer, and the learning rate for that, my default would be 1e minus 4. So these are like my default values. Then we're gonna start with the training. So first of all, we're gonna have our callbacks. So here we have 4 callbacks. Okay, first is the model checkpoint. So in this model checkpoint, we first give the model path. Okay, this what basically it does. It basically checks your validation loss. Okay, we specify a validation loss here, so it's going to check that, and if there's a decrease in validation loss, then it's going to save the model checkpoint or the wait file. Okay, so that is how wait file is going to be saved. If the validation loss increases, that means the performance is not good, then it's not going to save that wait file. Okay, then it has reduced LR on plateau, so it is gonna again monitor the validation loss. So if the validation loss does not decreases for 5 continuous epoch, then it's gonna decrease the learning rate by this factor. Next we have CSV logger. So it is going to write down all the training loss, validation loss things into a CSV file, so that we can later check it and you can use it to build graphs. Okay, maybe you can use TensorBoard also here, but I don't prefer that. I just need this simple CSV file so that I can do things on my own. And at last we have early stopping. So this is basically a mechanism to stop the training, because if you see, I've specified 100 epoch. Like in my experiment, usually for research paper, I specify 500 here, just a large value, and I use this callback early stopping to stop the training. So what it does, it also checks your validation loss. So let's say for a continuous of 20 epoch, your validation loss does not decrease, then it's going to stop the training. So this is my mechanism to stop the training. Okay, now let's just call our last step, that is model.fit. So in this, we're going to provide first the training data set, then the validation data set, number of epoch, and the callback, and the training part is done. Now what you can simply do is you can execute this file and the training would begin. So let's hope we don't have any error in it. That would be really good. And if we have any error, then we can just solve it. Okay, so we don't have any error, but here you can see it's going to take 18 minutes for 1 epoch only. So we can let it train. We can see how it processes. Okay, let's now work on the test then. Okay, because till then we can work on test, and maybe it can done with 1 epoch. Okay, or what you can do for yourself, if your GPU is not that powerful, you don't have that much computation power, you can decrease the samples in all the 3. Let's say you can use 100 here, then 500 by 500. Okay, like, but maybe class imbalance would be there. Okay, because eyes are really small and those kind of things. But for your own like just purpose, you can adjust the data set. So let's continue working with our test file now. So in the test file again, we're gonna first of all import all the things. So we're gonna simply copy paste them. So here you see again same line, just to remove all the TensorFlow lines, and like those are like unwanted things. Then we have NumPy, OpenCV. Here we require pandas. Okay, then we have globe to extract the image and mask. I don't think we require globe. Okay, I'll just import it, just leave it for now. Then we have TQDM. I definitely know this we require because this is the progress bar. Okay, then we have TensorFlow. This is our framework in which we have implemented the code. Then we have matrix. Okay, these are to compare, or to not the compare, just to evaluate. These are 2 different matrices we use to compare the segmentation mask with the ground truth. Then we have imported 2 functions from the train file, that is create dir and the load dataset. Then again we have these global parameters. Okay, now we're going to move on to this main function. So first of all, we're going to have the same seed value, that is 42. I've already told you why, so that we have same randomness. Then we're going to create a blank folder called results, so that we can save our image, ground truth, and the prediction, and we can compare them just to visually see them. Then we're going to define some hyperparameters which require here, that is image height, image width, and number of classes. After that, we need some paths, that is the dataset path and the weight file path. Okay, this is the dataset path. Then we have model path, that is our weight file that would be saved, okay, when this first epoch is done. So it's still 15 minutes are there, and I think it won't be completed. We can, in that meantime, we can complete this test file and it would still remain there. So let's do one thing. I'll just stop it because I only have a weight file which is trained on 5 epoch, like, yeah, 5 epoch. We'll just use that. Okay, so don't worry about that. This is just a demonstration to show you because it's going to take a long time, so I'm not going to do it. Next we have our RGB code and the classes name. Okay, after that we are going to load our dataset. These steps are like repeating, so you can directly copy paste them from the training part. Okay, that is I also do. Now comes our main part, that is we're going to load the dataset. Not the dataset, that is the model. So we're going to say model tf.keras.model models.load model, and here we need to provide the model path. And if you see, we don't have any weight file. Let me just show you. Yeah, beautiful. We don't have any weight file. So I've already trained this, and we have this weight file here. So we're going to copy this model.h5 and the data.csv. Just don't look at this now. We will have this file, but not now. Okay, so we have the weight file now. Okay, so let's do one thing, load the weight file and print the model.summary. So this is the trained weight file. Okay, so you can see it is a trained model. Here you can see the test, not the test, the split, the dataset split, and here you can see the model. So there's no problem here while loading the model, so we can remove this step. Next we're going to work on the evaluation. Okay, so first of all we're going to have the prediction. So we're going to say prediction and then evaluation. Okay, so we're going to start with a blank list called score. Okay, but I'll use, I just give some space here like this. Okay, so this is a blank list which we're going to hold scores of, like the each image and mask. Okay, then we're going to loop over our test set. Here we're going to write zip, then test x, test y. So this is not correct. Yeah, we have test x and test y. Then total, a parameter for the TQDM. So it's going to take the length of the data set. So basically total means how many times the loop is going to iterate. So first of all, let's print the x and y. This is the path. So path may look different for each system. Okay, like, so this is, I'm working on a Linux system, Ubuntu. So this is my path. Maybe if you are in Windows, those slashes would be different, and that is what gonna cause error. And this is not gonna run in first time, I'm saying you, because I have a lot of issues with people who says that it's not working on my Windows system. That is because the path is a kind of like an error causing thing in mostly in Windows. Maybe in Mac, I don't know whether people use this in Mac or not, but I definitely know people use it in Windows and they have troubles with this path. So this slash is going to be different in your Windows system. Okay, so these are the path for image and mask. So what we need this name, just this name. So we're gonna split this string on the basis of this slash. So just remember, this is slash on my system. Maybe on your system the slash is different. So slash is basically a character that separate your folder name and files. Okay, so now what I'm going to do, I'm going to say name equals to x dot split, and I'm going to paste that slash in. Now just see, we would have a list. Here you can see the list, and if you go to the last, you can see we have the name with extension. So we're going to say -1. -1 refers to the last. So you'll see we have the name with extension. You can even work with this, but let's now separate these two. So this is now, I think it is really simple. We have this dot separating these two. We'll say split. Again, we're going to split it on the base of dot. We again have a list with name and extension. Now name is in first place. So let's say 0. Now we have the name, just the name. You can give any extension, whatever you want. So the name also help us to recognize it with what is, help us to match it with the original data set. So this is extracting the name. So let me write a line at the top of this. Next we're gonna read the image first. Okay, so this is the image, that is X, the path of the image. We read it as RGB, then we resize it, then we save a copy of this resized image, then we normalize it, then we expand its dimension. So let me just give you some hint here. Let's say it would be height by width by 3, because model take images in the form of batch, input in the form of batch. So it is only one image, so it would be, this would add a dimension on the first axis on the 0. So basically first it would be like 1 by height by width by 3. So this would be like a batch of one image, and then we're going to convert it to float 32. Next we're going to read the mask. Same way, just reading it as grayscale, resizing it, convert it into integer 32, and we are done. Now let's print the shape of both of them, and they both should be of 512 by 512. And see, it is an image of batch 1, 512 by 512, a mask of 512 by 512. In the mask we don't need any channel or any extra thing, because the model is going to take image as the input, not the mask. Mask is just for the training, okay, and in during testing it is for the comparison, okay, just to evaluate it. Like this is the prediction, this is the ground truth. How much difference is there in between the two? How much similar they two are? Okay, this is why we use ground truth. Then we're gonna have the prediction. Okay, so we're gonna say pred, that is the prediction, model dot predict. We're gonna give the image, and here you're gonna say verbose equals to 0. Now we're gonna print the shape of our prediction. Because the image, the batch only contain one image, so the prediction would also contain one mask. Yeah, it is. I'm just checking whether it is saved or not. You can see only one image, or only one mask with 11 classes. Okay, now what we're gonna do? So first of all, let's extract this one mask by simply saying 0 index here. Then what we're gonna do? We're gonna pass it through the argmax. On the last axis, that is -1. Now if we are not familiar with what argmax does, so what it does, let's say you have a list, let's say you have different probabilities, let's say you have 4 class and their probabilities are, let's say 0.1, 0.2, 0.1, okay, then at last, so it became 0.4, these 3 total, and the last became 0.6. So when the prediction is passed through a softmax activation function, though, so that would give you probabilities over the class. So let's say probabilities are like this. This is for the class 1, class 2, class 3 and class 4. So when you sum all the probabilities, it should become 1. So what argmax does, it gives you the index number of maximum probability. So here in this case, it would be 3 as the index number with maximum probability, that is 0, 1, 2 and 3rd. So that is what argmax does to the prediction mask. So this is basically 1 pixel, okay, I am giving you with 4 classes. So this is what is done with the prediction mask, and we get a normalized mask with like pixel values from 0 to a number of classes. Okay, let's run it again and see the shape of the mask. Can see it became 512 by 512. Now what I'll do, I'll save it for you here. Or okay, let's do one more thing. Before that, let's print this prediction just to show you. Just maybe we will see different pixel values from 0 to 10 plus 1. Maybe we'll have some different way. Okay, here you can see everything is 0 0 0. Okay, let's have a different way. So we're gonna print the unique numbers inside this prediction. Now you can see, so this mask contain all the 11 classes from 0 1 2 3 4 5 6 7 8 9 10. Now you can see this is normalized, and that is same as our ground truth mask is. Okay, now what I'll do, I'll just save this one sample for you, and I'll also show you a way how you can visualize these normalized masks in grayscale format. Let's say this is the name of the image, the mask which you're gonna save. Now you have pred. Now you know the number of class. So if you save it in this format, it's not going to be visible. So what I'm going to do, the maximum pixel value is 255. Divide it with number of class. Okay, and then we get a factor when we divide 255 with number of class and multiply that with prediction. Okay, now we're going to save it, and I'm going to show how this mask look. So let it run. Okay, we have something. Okay, this should not be print, it should be cv2. I am right. See, I have done again these stupid mistake I used to do, because like making long videos, I lost my focus. So if you have reached this part of the video, make sure to subscribe the channel. Okay, now I'll show you the prediction mask. See, this is the prediction mask, and from this prediction we can easily see this is the face and this is the second phase, but the second phase is not that good, but the first phase is really good. Okay, so when we save those results, we can compare them with the ground truth. That way we can easily see how much our model is able to predict the things right, and you can even see how the things look. Here looks white and gray and everything. Now let's remove this line. This is just to show you. Okay, I'll just leave it here. Maybe you can use it in future. Now what we're gonna do, we're gonna save the results, or you can say save the prediction. Save the results. So we have a save image path where we're gonna save our image. That would be results slash name that we have extracted at the starting in this extension. Then we have a function which we're going to build image, then mask, then prediction, then save image path. Okay, so if we remember, we also have the RGB code. Until now we are just viewing the mask in the grayscale only. Now let's also learn how to save those normalized masks into RGB, because that is important when you work with research papers. So for a bit I'll just comment it down here and we'll work on that. So what I'm going to do, I'm going to build a function. So let's build a function. Let's call it grayscale to RGB. Okay, first of all we're going to give the mask this our pred. Okay, let's call it pred. Yeah, that's the spread, not call it. That is the prediction mask. Then we're going to give the classes, not the classes, the RGB code. Sorry, RGB codes. These two things we require. Let's go to the top and try to build this function here. Def grayscale to RGB. Going to take the prediction mask, so let's call it mask here. The RGB codes, okay, should be RGB codes. Okay, so we are done. Now this is a bit tricky here, and it's really easy. Okay, this is like the thing which I have like struggled to do it. Even initially I don't know, like even I face difficulty with multiclass, then I learn, and I finally at one point I realized that it is really easy to convert from grayscale to RGB. Just you need to just think it deeply and you will get it. So we know the output would be in RGB format. So let's save the height and width. Okay, first. So we can say mask dot shape 0, mask dot shape 1. So these are the height and width. Now let's convert mask to integer 32, specifically integer 32. I'm doing it. Maybe it is already done, but still I'm gonna change it to integer 32. Okay. Next, a list, empty list. Okay. In this, we're gonna save our RGB pixels and then we're gonna reshape them back. So what we're gonna do? Okay. So we're gonna have we're gonna loop over our mask. Just wait it. Oh, there should be a space for I pixel enumerate, and we're gonna give mask dot flatten. So here you see we have flattened the mask. So now it's a list. Okay, and with each iteration we're gonna extract that pixel value from that list, and that could be from 0 to 10. Okay, so just remember that 0 to 10. So those are the pixel value, and if we use those pixel values as the index number to the RGB code, let's say we have 0 as the pixel, that would refer to background. So we're gonna use this RGB code, and in the 0th index number we have the RGB code for background pixel. So that is how we're gonna do it. It's really simple. Just we're gonna say output, that is our empty list, append. We're gonna append the RGB code. Say RGB code and then pixel. So now I'll tell you why I've converted it to integer 32, because when you index you require integer, not float. Okay, now we have all the RGB code as a list. Now what we're gonna do, we're gonna reshape it. Output np dot reshape the list, we need to reshape. Then that is why, if you remember, I've saved the height and width, because we flatten the mask and I don't know, so I just saved them here. Okay. So this is our RGB mask. See, it is really easy if you just think a bit, and it's really easy. Like this is the difficult part. I've faced difficulty and I'm not making videos on multi-class segmentation because even I am facing difficulty. Like when I have not solved the problem, how can I just present you something which is not yet done? So that is why I'm just uploading videos on binary segmentation. But now I'm just ready to have videos on this multi-class segmentation. So we're gonna call it RGB mask. Let's save it again. Oh. So this time we don't yeah, let me just put this. Okay, I'm just doing mistakes. Why these two cursors here? Okay, let's do it that way. Okay, now this is really easy. So we don't need this, and we don't need pred, we need this RGB, and nothing we need to multiply it with. So we're gonna save it, run it, and see if we have any error, because error are a part of a life, any program thing. Okay, it's done. Finally we have our RGB mask. See, that's really easy. Now you have the RGB mask, and it looks much better than the grayscale one. Like if you present it to a present it to a paper, that would be much better when compared with grayscale. Like colors are an important part of human life, so grayscale is worse and RGB color are much better. Okay, so we have learned this thing also. Now we're going to continue with our saving the mask and whole lot of thing. Okay, so now we need to define this function. So what we are doing, we are saving the image, ground truth mask, and the prediction in this specific path. So let's define a function here. Okay, so now what we gonna do, what I'm gonna first print the shape of image, mask and the prediction. Here you see image have three channels, but mask and the prediction don't have three channels, they have one channel. So we need to make sure that each of the image that we want to join together should have same number of channels. Okay, because their height and width are going to be same, that is not an issue, but the issue is with the channels. So what I'm going to do, I'm going to say mask np dot expand dims prid, and we're going to expand the dimension of on last axis. Now what I'm going to do, I'm going to print the shape of mask and see what happens. So we have expand the dimension. So when you expand the dimension, by default one is added. Okay, because we are simply reshaping it here. Now what we're going to do, we're going to concatenate this mask 3 times over each other on the last axis. Mask, mask, mask on the axis -1. I'm going to save it and let it run. You see, now we have same number of channel as the input image, and same thing when you copy and do it for the prediction mask. Okay, so our mask and predictions are done. So let's now save. If you see, we need to save 3 images: image, mask and ground truth. So let's have a simple white line in between them, that is separating them. So we're going to say line to np dot ones, okay, an array which contain 1 as the value. Now we need height of image, let's say image dot shape 0, then 10 as the width of that line, then 3 as the channel. So this line should also have same number of channel. Okay, because we are concatenating all those images on the height wise, okay, on the like width wise. No, I'm just confused. Okay, let me just do it and show you. You can write it down that is height wise or width wise. Like I got confused between horizontal and vertical. np dot concatenate image. Okay, it should be image x. Yeah. Oh, here also it should be image x. Got an error before executing the code. Line, mask, line, and then the prediction. Axis should be 1. Then we can save it. cv2 dot I am right. Save image path. Then cat images. Now let's run the code. Just remember the sequence. It is image, ground truth and mask. So it is done. Now we have this results folder. Okay, so if we now see, we have both the ground truth and the mask, but in grayscale format. Let's now do one thing. Let's now convert them to RGB. Okay, so remember, how do we convert them to RGB? So this is like a mistake from my side. Instead of doing this, I should have used this function. And here we say mask. This is kind of big mistake. RGB codes, same, grayscale to RGB, red. Like, I'm sorry for this mistake. Like, even I'm laughing. Like, this is what happened when I like make long videos. At the end, I got really confused and I start losing my focus. Like, but I feel like I should make like continuous, because once you start a video, you should do it. Otherwise, it's gonna be left. And then those days would convert into weeks. I do a lot of mistakes. Okay. Mask, 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 then prediction, 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 prediction. Okay, now it's fine. Let's run it again. I hope I'm not going to do any more mistake at the end. Okay, now you see the result. Now this looks more beautiful and viewable. In the image you have two face, but in the ground truth you have one. And in the prediction, like see, our model is doing well. Like the model is shown only one face, like in the ground truth, while okay, but it try to predict another face also. Even if you see the nose, it is accurately predicting it. Like rest of the things it's not predicting. Like the face and nose is a bit appropriate, and a bit of upper lips and a bit of eyes, but things are messy here, but it is able to predict the second face also. So this is the visual results. Now we're going to move on to the matrix, that is F1 and Jacquard. Okay, let's first of all we need to flatten the array, both the mask, that is the ground truth mask, and the prediction. So we do mask dot flatten, pred dot flatten, simple. And we need labels, that is a simple list. Okay, starting from 0 till 10, 0 1 2 3 4 5 6 7 8 9 10. Next we're going to calculate the matrix value. So we have used two matrices, that is the F1, or you can say the dice F1 and the Jacquard. Okay, we are given the flattened mask, prediction, and just remember they both should be an integer. Okay, just remember that they both should be integer. So let me just convert it to integer here. Okay, now let's see if that work or we get an error. So what we're going to do, we're going to print the F1 value here. So it's going to give the F1 value for one image for 11 classes. So here you can see F1 score for 11 classes. First background, then another, all those classes. So like this, we're going to have the Jacquard for all those 11 classes. So what are we going to do? We have is empty score defined at the top, an empty list. We're going to append all those value inside it. First F1 value, then Jacquard value. Okay, this is we're going to do for the complete image. So after, let's say I remove this break here. So we have an array. This is the score. Let's convert it into a numpy array for easy. Let's do it small because we also need it later. Maybe we need it later, so I'm saving it here. Now we need to find the mean score. Okay, before that, what I'm going to do, I'm going to reduce the test image, because there are 2000 images and that's going to take huge time. So we're going to do it for 10 images only. Okay, and 10 mark, because doing it for 10 is easy. Like doing it for 2000 you need to wait. Let's do it for 10 if it runs or any error. Okay, till now it's done. So let's, even for 10 it take 5 seconds. So within 1 second only 2 samples. So you can see for those 10s we have these. Okay, this result is perfect, I can say. Like this is really good. Within 5 epochs you get this result, and I'm really happy with that. This is also good, but from this hair side it's kind of bad. But we have trained it only for 5 epochs, and I'm happy with just the result we have with 5 epoch. Like these are some of the nice and cool predictions we have. So let's keep them aside. So this code runs really fine till now. Let's now print the shape of the score. So just remember, we have 10 samples. Okay, we have 2 matrices, and we have 11 classes. Okay, just remember this and then see the shape. See, 10, 2 and 11, 10 samples, 2 matrices, 11 class. So what we need now is a mean. Okay, mean F1 and mean Jacquard over all those classes. Okay, not all those classes, but over all those samples. So now let's calculate a mean F1 and mean Jacquard. So we're going to say score is to np dot mean, and you're going to say score, and we need mean on axis 0. Axis 0 means these 10 samples. Now let me just print the score for you here, and we also print its shape. Let's run it for now. So here you see the shape is 2 by 11. So we have the mean score, and here first we have the f1, then we have the Jaccard over 11 classes, and I see mostly like good score here, like 51, 50, because 5 epoch I take this as a good score. Let me just remove these. So now what I'll do, I'll open a CSV file here, because we also going to save the result in a text file also. File score.csv, we're going to write it, and we have 3 columns here. First class name, f1 score, and Jaccard. Okay, now we'll sprint. So we'll do 2 things. We'll print the things on the screen, we'll write them to file also. So here we write them to file, and now we print them on the screen. Now see what happened, what we'll see on the screen till now. So till now we have these things on the screen, and we also have is this score.csv file. For now it is blank, just these 3 columns. Next we're going to calculate the values and save them to the file, and also display them on the screen. Okay, so if we remember the shape, it is like 2 by 10 plus 1, 11. 2, that is number of matrix times number of classes. So what we need now, we want to calculate f1 and Jaccard for each class. Okay, so let's print it on the screen. So we're going to say for I in range, so we can say num classes here. So first of all we need is a class name. We can have from classes index I, then we need f1 from score. So first we have appended the f1, then Jaccard, so it would be in 0th index. Then for class I, not it's 0, then for class I we want class I, you means first class 0, class 1, class 2, class 3, like this till class 10. Same way we have this Jaccard score index position 1, and then I. So we have this. Now we're going to print it on the screen and write it to the file. So let me just save it and run it. So here you can see the classes, it's f1 score and Jaccard. Like background is really nice, 98, 96. Like the skin is also good. Like the mask which have large areas would be really good, but when your areas the mask gets smaller, your performance would also get lower. See the eye 53, 59 left, like eyebrow eye 51. We see inner mouth, which is really small area, so it is very difficult to segment that area. So that is why the inner mouth score is lower. And also just remember, it's only trained for 5 epochs. Okay, so we have these scores. Now at last we're going to calculate the mean score, like mean f1 and Jaccard over the classes. Okay, let's do that. So I'll print some lines here. This is basically a dash, this dash I've added. Next let's calculate the class mean, np dot mean score. Now we need to calculate mean in the last axis, so we're going to say -1. Class name is mean, so we have f1 as class mean on 0th index, then we have Jaccard on class mean on index number 1, and then we're gonna print them on the screen and write them back. Okay, and at last we also close the file, that is the CSV file. So let it run again. So this is the performance just on 10 samples. Okay, so here you can see we have a mean F1 of 71 and a mean Jacquard of 61, and that is really good performance. Okay, I like, for me, because I write research paper and I know what the good performance, what the bad performance is, and this is a decent performance because what we have is 5 epochs, and that too a baseline architecture like UNET. We don't have any good architecture. Let's say we have not used transformer till now in videos. Maybe in future we'll use this dataset with transformers also for segmentation, but with this dataset and 5 epochs, it's really nice performance. And also segmentation mask score also look good. So now I'll show the score with complete dataset which I have calculated. So what I'm gonna do, I'm gonna remove it from here. Okay, so I'll also show you. So this is the score on 10 samples which is also saved here. If you see, just want to, I just want to read. Okay, from there, see classes that F1 and Jacquard, and also we have this mean. So this is really nice because we have saved it. Now we don't need to run those whole the testing again. So now what I'll do, I'll just copy this core file, paste it here, replace. I'll just show you. Now this is a score on the all 200 samples. Okay, you see it as 70 as the F1 and 59 as the Jacquard. How much difference it is? 71, 61. So it is not that different. It's near about the same. So this is the test score which you have got over those 200 test samples. Okay, so this, I think this marks the end of this video, and we have successfully completed the human face segmentation project, and that too really easily. Okay, just I think it's about near about 1 hour 15 minutes of this video, and you will learn completely about the multi-class segmentation. If you are really new, then it's going to be really exciting for you because we do all the things from scratch. Okay, and if you have reached till this part of the video, make sure you subscribe the channel, like the video, share it with your friends, and if you have any question, just write it down and I'll try to answer all your queries. Or if you want me to build any other architecture or do any video, just write it down. That also I'll add it to my list. If I don't know it, I'll learn it, then make a video. If I already know that thing, I'll just make a video very soon. Okay, so thank you, have a nice day, and do subscribe the channel and share the video once again, please, because I'm working really hard for this channel for now. I'm like really very serious from the last 1 month. If you see, I'm like uploading 2 videos for the in a gap of like 10 days. Within 1 week or 8 days, I'm just putting 2 videos at least. Okay, and I'll continue this. If I don't have any exams or anything in my house, I'll just try to put at least 2 videos per week. Okay, so just support my channel, and I just want one thing, just support that channel. I know I want subscriber views also. Okay, so at the end I'm saying just subscribe it. Thank you.